to the cloud. Okay, good. Share screen. All right. Okay. So as I was saying, whenever I give a talk on tree methods, inevitably somebody will raise a hand and say, aren't tree models unstable? You may have heard of that, right? That is a half-truth that's been perpetuated, I think, starting with Leo Breiman. The criticism is that in a tree, if you change the data a little bit, then the tree may change. Okay, but it happens with all methods, including linear regression, right? In linear regression, you change one variable, the coefficients will change. You change some data points, the coefficients will change. So, this so-called instability is not unique to trees. Just that maybe with trees, it's more apparent because you see the picture, right? And people, because of that, people say they prefer random forest. But random forest is random. It's worse than unstable. It's random. So unless you lock the seed, you cannot reproduce the random forest model again. It's random. Okay. So, but nonetheless, it is true that the tree models can change. It's just like if you take a picture of me now, all right? Take a picture of me here, and you get a picture of me, a fairly truthful picture. If I turn a bit, you get another picture. You put the two pictures together, you find that they are unstable. The two pictures are not the same, right? But whenever we want to take pictures, we take multiple pictures because we do want to look at different angles. And so in this example, I decided to, try another variable to split the tree first. Okay, so in this tree, the default method chose H as the first split. And then I now change it to renal because we saw that renal disease seems to be a good predictor, right? So if I told the algorithm to use renal disease to split first, it will split on renal disease. The left side will be people without renal disease. The right side will be people with renal disease. And now you see H coming back again, right? And then you see Charlson score. So we saw Charlson score here, right? So in this tree, the H, Charlson score, and renal disease, we have three variables only here. And here we have the same three variables. But we have one more, congestive heart failure, right? Now these two trees look quite different, right? You agree? I put them side by side now. They look quite different. The first one is on the left, the second one on the right, but they're actually the same, almost the same. The node colored blue is the same node as this, all right? Just that the conditions going to the blue node on the left splits on H first, then renal disease. So basically the path on the left says that if your H category is less than or equal to 1, meaning 0 or 1, you go to the left if you do not have renal disease. Well, there's the same path actually. The path on the right is also the same. You can actually see that by looking at the sample size. The sample sizes are exactly the same. So they're the same observations. Okay. In fact, the only difference are the yellow nodes. In this case, there's one yellow here, and this is split into two. Right? So while visually it looks that the models are different, and you claim that they are unstable, they are actually telling the same story. Right? And why is it that on the tree on the right, we have two more nodes? That has to do with cross-validation pruning, because the algorithm actually grows a huge tree until either the nodes are pure or there are too few observations, okay, or all the variables have been exhausted, and then uses cross-validation to prune. So sometimes because of the cross-validation seed, you may get a little bit shorter, a little bit longer, right? So I hope this will set aside people who claim that trees are unstable. They are unstable to the same extent as anything else is unstable. On the other hand, here I give you an example of two trees that look different, but they're actually the same. Okay. All right. So another thing that you may want to know about this is, so you see that we have about 20 odd variables, 3 or 4 here pop out. People in explainable AI, there are a lot of people working on so-called explainable AI, trying to explain deep neural nets. I think they have a big problem. But anyway, what they are trying to do right now is maybe rank the variables in order of predictive ability. So the algorithm that I'm using here, guide, also can rank them, and here are the important scores. So later on in this sequence of lectures, I will hope to talk about how these are computed. And you see the biggest, the most important variable overall is renal disease. Second is age category. Third is Charlson. And fourth is congestive heart failure. And all the rest come down. And they're colored in terms of orange, yellow, and blue. The orange ones are basically like 99% confident. So there's some sort of confidence level associated with this. Yellow is like 95% confident. Those in cyan or blue, on the screen looks like blue. That's just the last one, that's peptic ulcer disease. That is considered to be equivalent to noise as far as its predictive ability, right? So now, in a situation, most people who don't know about trees and think they want something interpretable, they will reach for logistic regression. Right? That's a very common thing. I think there are already hundreds, if not thousands, of papers published in the medical literature on COVID-19. This is more than 2 years already. And the majority of them use logistic regression. Well, for this data set actually is very simple. There are no missing data. That missing data will throw a big wrench into the problem. In this problem, we cannot include Charlson score because Charlson score is a mathematical formula derived from the 0-1 comorbidities. So Charlson is exactly linearly dependent on those 0-1 variables, there are 21 of them, cancer, renal disease, and so forth. So if you use logistic regression, you either have to just use Charlson score and throw away all the individual pre-existing conditions, or use only pre-existing conditions and throw away Charlson score, right? You saw in my trees, I don't have to do that. I have Charlson score appearing together with renal disease, okay? There's no problem with collinearity in the regression tree because this is a piecewise constant regression tree. I'm not fitting any kind of linear models. The other problem with logistic regression here is that there's a group of patients who are grouped under American Indian, Alaskan natives. None of them died in this sample of 31,000. None of them died. As a result of that, logistic regression will not converge. One of their beta coefficients will go to infinity. It's got quasi-complete separation, right? So if you want to use logistic regression, you have to rule out Charlson score and rule out this sample size, this group of people, which is not really big, but you have to rule them out. Whereas with the regression tree, you don't have to do anything like that. And here's the result from logistic regression. Okay, so I highlight in yellow those that look very significant, 10 to the minus 16, the p-value. So this is straight from R. And you see the age category is very significant. Age is very significant. Everybody knows that. Sex is also very significant. Males are more likely to die. Race, one of the races has to be set to 0. That is the alphabetically first level, which will be Asians here. Okay, because American Indian, Alaskan Native, that would have been the first level that would have been set to 0, but that had been excluded. So the next alphabetical word is Asian. So everything is compared against Asians, right? And you see that, blacks are, that's significant. Blacks are more likely to die compared to Asians. Then you have AIDS and so forth. And so you have congestive heart failure, which we saw in the regression tree, chronic pulmonary disease, was not picked up in the regression tree, but you pick up all these variables. All right. Of course, renal disease, is super significant, right? And why do people use logistic regression? Because they don't have anything else to use. And if you want to have some statistics in your paper, in a medical paper, you need to put in some statistics, so they throw in logistic regression. But this model is almost surely wrong, because this model is additive in the log odds. Okay, so there are no interaction terms. Why are there no interaction terms? Because if you have interaction terms, you cannot interpret the coefficients as easily. So here, renal disease has a beta of 0.769. You take the exponential of that is about 2.1. That means the odds of a person with renal disease dying compared to one without renal disease is about twice. Okay, so that's why people like to use logistic regression. But logistic regression, just like anything else, is notoriously unstable. You change some data points, the coefficients will change. You throw in some additional variables or take out some variables, they will change. So actually, I always tell students, it's very dangerous to interpret the coefficients of even a linear model, right? But people just do that. They look at the coefficients, they take exponentials and say that's the odds ratio. So just to revisit an example from John Tukey, suppose look at linear regression. Suppose we're trying to predict the height of a person. And we have, this is the right arm length. Right? So if you fit a model to x1, maybe you get this. 2.2 x1, maybe a pretty good fit, right? And so if you interpret that model, you will say, well, yeah, for each inch of length of the right arm, you go up to 2.2 inches of height. If you use both regressors, you may expect this. Right? Okay, so now if that's what you got, then what is the effect of x1 adjusting or controlling for x2? The effect is 1.1, it's halved. If you don't have x2, the effect is 2.2. If you have x1, the effect drops to 1.1. If you're lucky. If you're not lucky, you might get this. 0.7. You might get this, because x1 is essentially x2. It's the sum of the coefficients that matter. As long as they add up to 2.2, right, you get a good prediction. So this is because of collinearity. So it's really treacherous to try to interpret coefficients from a parametric model when there's collinearity, right? So for example here, suppose we have x4, x3, which is the length of right leg. Then now if you put in x3, these coefficients will change, right? So that's the difficulty with, that's my knock on so-called explainable AI. It's really even hard to explain linear regression. Linear regression is great for predictions, just like logistic regression is, but if you try to explain it, it's really hard. And so here's an example, to show you how much correlations there are among the predictor variables. I highlight in yellow those that are sort of fairly high. So the correlation between Myocardial infarction and congestive heart failure is 0.38. Correlation between renal disease and congestive heart failure is 0.40. So we saw in a tree that renal disease and congestive heart failure both appear. All right, and they both appear in the logistic regression model, but they are correlated in the regression model. They are not. They are still correlated in the tree model, but that doesn't hurt it because we're using one variable at a time. Okay, so all right, now so that's my knock on logistic regression, but suppose you really don't care because the rest of the world is using logistic regression. Right? You interpret the coefficients this way as taking the exponential of that and say that's the odds ratio. And the referees will accept it and get a paper published. Okay, if you accept that, then the only thing left that you should fix for this is to fix the model. This model is wrong. It should have interaction terms. It does not. The reason why we do not put in interaction terms is because if there's an interaction term between x1 and x2, then you have an x1 term by itself, beta 1. And then you have an x1, x2 term, which is beta 1, 2. The effect of x1 is now no longer just beta 1. You have also that x1 part in that cross product. And you cannot pretend the whole x2 constant. And then, so it becomes a real mess. But an alternative to that, if you really want to use logistic regression and you don't want to touch interaction terms, is you fit a logistic regression tree. In a logistic regression tree, every node has an additive logistic regression model. No interactions. The interactions are absorbed by the tree structure. Okay, so here I have 31,000 observations. I'm fitting 4 logistic regression models, one in each terminal node. Right? And in each terminal node, I'll show you the results of those logistic regressions. They have no interactions. If interactions are needed, that node will split further. Okay, so the goal here is to have a tree such that you don't need, such that we will fit logistic regressions in every node without interactions, so that we can be more sure that we have taken care of the interactions. Right? So here, the first split is on age category less than or equal to 1, which is for people less than 60 years old. And if you're less than 60, then race comes in. If you're Black, or NHPI is Native Hawaiian Pacific Islander. That's a very small group, right? So they're mostly Blacks. Then you go into here, and this is just a very coarse estimate of the mortality. It's 2%. But these are young people. These are less than 60, right? If you are, so these are the Blacks, Native Hawaiian Pacific Islander. Otherwise, the whites and Asians and so forth go in here. And the risk of death is 1%. But if you're older, if you're 60 or older, then it depends on whether you're really old, over 60, or you're between 60 and 70. Okay? And then your risk goes up to 6% here and 15% here for people who are above 70. Now you look at this, you say, oh, what happened to all my pre-existing conditions? They're in the logistic regression model. So here I have 4 panels. Each of them gives you the coefficients for one logistic regression model. All right? And I highlight in yellow, those are sort of very significant. And you see that, for example, we know that renal disease is important. But if you look at the coefficients of renal disease, 1.37, 1.20, 0.71. They are not constant. They depend on age and whether on race for this side, and this is further on age. That's the interaction we're talking about. If there's no interaction, the coefficient for renal disease should be fairly constant across. Right? And now we discover them without having to throw in cross-product terms. Right? So you can see that liver disease here is significant, but it's not, in terms of p-values, they're not, liver disease is not significant. Right? But there's also something quite interesting. If you look at this carefully, and then I fit a standard logistic. I mean, that's what, it's as if it was pre-decided, right? But here we're using machine learning, so we don't pre-decide. It's unlike a clinical trial. I think whether it's in US or here, when you submit a request to do a clinical trial to the authorities, you have to state ahead of time what hypothesis you'll be testing, and you cannot test hypotheses that you have not pre-specified, because you have used Bonferroni corrections and so forth to control for them, right? But in machine learning, we don't have to pre-specify the hypothesis. I always feel it's very stupid to spend 5 years and several millions of dollars to collect data and not be able to mine the data, right? That you have to specify ahead of time what are the hypotheses you'll be testing, and then only test those hypotheses. The reason for that is because we don't know how to control for data mining. That is post-selection inference, which I will talk about hopefully later part of these lectures. Okay, and so that's why I highlight these p-values, right? They are very small, and they are very small because, oops. Because these do not take into consideration adjustment for multiplicity of tests. So in tree, you search for all kinds of ways to split the data, right? So to do post-selection inference, we have to no longer compare the p-values against this 0.05 level or something. We have to adjust, just like in the Bonferroni correction. Okay, so that's logistic regression tree. And incidentally, if you look at this this sort of standard thing, you see that, oh yeah, race is important, right? Race is important, and but you think that this is across the board. You think race is important across the board? No. According to this tree, race is only in here. Only among people who are younger than 60 years old does race matter. It's not that just because you're black, you're more likely to die. But that's what a linear logistic regression model will suggest to you, right? If you're above 60 years old, doesn't matter very much what is your race, okay? The reason is because if you're above 60 years old, the constant in the logistic regression model is so high already. In other words, once you are above 60 years old, actually here is above 70 years old, yeah, your beta 0 is already so large that your chance of dying is very high. That adding race and all these things don't increase your risk by a substantial amount. This is different if you use this model, right? If you use this model and you jack up everything, so you say that every pre-existing condition that is significant, I assume that person has that one, and you assume that person is above 80 years old. The predicted P is 95%. That's just completely wrong because it's just adding or multiplying the odds. All right. So because that's a lack of interactions. Okay. So let me now briefly talk about how these trees are constructed. This is there are two main steps. You just, first of all, you split the nodes, and you split using some criterion to decide what is a good, the best split. And then the key part, which many algorithms do not have, because it adds substantial computation time to the algorithm, is the prune. So many algorithms will have some sort of stopping rule, right? Whereas the algorithm I told you about, the guide, uses tenfold cross-validation by default, which means it grows a very big tree, and then it does it again 10 times using subsamples to determine what is the right size tree to have in this cross-validation mode and map it back into the main tree. Okay. So this is just a list of the algorithms that are available. So I'll just maybe save time by not talking about it. So let me get a little bit into the notation so that we can understand this a little bit better. So this is a little bit more technical in terms of notation. So Y is our class variable. So I'm going to start talking about classification, but Y now is a class variable. So it takes, it's like, you predict somebody's occupation. So it takes values 1, 2, 3 up to capital J. Pi J is the unknown population prior. Okay, so like I always wondered in the Fisher iris data that Fisher used to illustrate linear discriminant analysis. He had 3 types of iris flowers: Setosa, versicolor, and virginica, and they're equal numbers. And everybody who analyzes that assumes that the population priors are equal because they're equal sample sizes. And I don't know, you guys are in England. Are the Setosa, versicolor, and virginica flowers equally frequent in the wild? You know? Okay, wow, okay. So yeah, nobody knows that. So if you don't know that, you will estimate pi j, and you will estimate, if you assume that sample is a random sample, simple random sample, you estimate from the sample proportions, right? So n sub j at t, little t is represents a node. Capital T stands for a tree. T is the first letter of the word tree. I'm following the notation of Bryman's book. So nj is number of class J observations in node T. Nj without the T is for the whole sample. So you can think of it as a root node. And then pj comma t is an estimate of the probability that an observation is in class J and lands in that node T, right? And that's just a product of the prior times the proportions. And then the probability that an observation falls into that node is just a sum of that. And then this is a conditional probability that given that you are in node T, that you belong to class J. All right. And then for classification, we're not using least squares, of course. So there's a misclassification cost, right? If a flower is a Setosa flower and predicted to be virginica, how much does it cost me? How much does it cost me otherwise, and so forth? So this is a cost matrix. So they use a symbol capital C for cost. The resubstitution estimate is, so we want to find the best prediction for J at any node, right, at any one point. So the best one is to find out the one that minimizes the cost, right? So resubstitution means that after you find what is the predicted value for J or Y in that node, you use the same data to estimate it. That's why it's called resubstitution. You resubstitute the data that you use to get there. Of course, this is biased, but it's still useful for comparison between nodes, right? It's not useful as a real estimate of the true expected misclassification cost. And then for the tree, you just add it up and weight it by the proportions of samples in nodes. So nodes that have a lot of data will have a heavier weight, and nodes that have less data will have less weight. So now, to get these impurity functions, what do we consider an impure node? Well, it's best to think of when is a node pure? A node is pure if it is all Setosa or all virginica, right? Or all versicolor. Most impure is at the top root node when it's 1/3, 1/3, 1/3, right? So that requires some sort of a definition of an impurity function. So to follow the Bryman book, I use the notation I for impurity at the node. It is a function phi of the proportions of the classes at the node, right? And we want that impurity to be non-negative as well, right? So that purity becomes 0. So when they're pure, that's when they are pure, right? Only one component is 1 because it's all of that class. Then we want it to be 0, otherwise we want it to be positive. And there are 2 common candidates for that. One is entropy. And the other one is what is called Gini index. Right? The Gini index, in the case that you only have two classes, so instead of 3 types of flowers, if you only have 2 types of flowers, then the Gini index becomes equal to 2 times the binomial variance. So it's a reasonable measure of heterogeneity. Right? That's for classification. For regression, we would usually use sum of squared errors, or if you want to use logistic regression, we can use the binomial deviance. Right? So these are just impurity measures. So here's the cut method. So I'll first tell you what the cut method does. The cut method is a super greedy approach, which actually the first time I saw it, it's like, it's obviously the right way to do it, right? So given a split variable, say x1, you find the set of splits on x1, right? And the splits have these forms. If x is ordinal or continuous, then that x is a line from minus infinity to infinity, and you cut the line, right, into a half line. If it's categorical, so that if x is occupation, then you look at all possible subsets of occupations, right? Could be just one occupation going to the left, all the other occupations going to the right, or just 2 occupations left and all the rest to the right. So that's categorical. And for each of these possible potential splits, so you search over all these splits, you compute what is the goodness of the split, is how much the impurity is decreased by that split. Okay, and then it's a matter of just choosing the best split and best x variable that makes the goodness of split maximum. Right? Okay, so so it's very simple, very neat, but it has some problems, and that's one reason why people don't use CART so much nowadays, or RPART. RPART is a clone of CART. The problem is that if you have an ordinal x with n distinct values, like age, you know, in the COVID data, we have 31,000 observations, and the ages go from 18 to maybe 99, right? So how many unique values are there between 18 and 99? Less than 100. So how many ways can you cut this age axis? Right, less than 100 times. Okay. If you have a categorical variable like sex, there's only one way you can cut sex: male one side, female the other side. Doesn't matter which side is which, right? Because given the tree, I can go behind the blackboard and look at the tree, you know, flipped. So with a binary variable, there's only one way to split the data. But with ordinal variable, you could have many ways to split the data. In the COVID data, we don't have a categorical variable with a lot of values because they're all 0, 1s. But suppose we have these patients coming up with postal codes. Right? Everybody has a postal code. And suppose everybody has a different postal code. And you're trying to find how good can I split on postal code for these patients to predict death? Well, that's very easy. If everybody has a different postal code, you just find out, take the people all of whom that died, and that's a set of postal codes. But if you run it, you get a pure node and finished. There's nothing left to split. On one side, everybody died. On the other side, nobody died. Right? That obviously is a nonsensical split. But that's because we allow so many ways to split. There's an exponential number of ways to split on a categorical variable. Right? So that's one thing we mentioned the last lecture, talking about whether a model is easy to interpret. The tree model is easy to interpret, but the tree model is also very easy to misinterpret. So if you have a split on postal codes, and you find that it's such a powerful split, you start to think that spatial information, that is COVID-19 is somehow, so people will come up with all kinds of theories, but why some postal codes tend to have people who die, well, more likely to die than other places, right? So that's just because of selection bias. So, so that selection bias is one thing. Second thing is computational, because if you have categorical variables with many categories, then it takes a long time to search for the splits, because for every split on a categorical subset, you have to evaluate the impurities, right? Also, this precludes the possibility of fitting, for example, a logistic regression model in each node. Because if you follow this approach, for every possible split, you fit 2 logistic regression models. Then you move the split point. You fit 2. Move, right? So that can be totally excessive. And with this approach, nobody has been able and would be able, unless computers become super fast one day, to fit non-constant models, unlike the logistic regression tree that I showed you, which of course doesn't use this approach. So this bias towards selecting X variables that have more splits, mentioned in one sentence in the Card book back in 1984. They do mention that, but they did not discuss it. And so nobody sort of noticed it until a few years later, I have a student start looking at this, and then we discovered, yeah, there's this problem. So we come up with an approach that would basically try to select the X first before we find the split point. Right? So if a variable is not going to be selected, what's the point of, why waste time to find the best split on that variable if that variable is not going to be chosen? So it turns out that because we were trying to save time, it turns out that we solved the selection bias problem. There's also this problem about selecting X with more missing values, and we'll talk about missing values later on. Okay, there's a shortcut method though, if you only have 2 classes, that this computational, exponential computational amount does not hurt you. And that is, you can rank so suppose we are trying to predict whether somebody dies or not, like COVID-19, right? And we have occupations. You don't have to search over all subset occupations. For each occupation, you look at the proportion of people who died, say students, military people, and so forth. And then you sort the occupations in terms of the rate of death, and then you just cut along that thing. So basically, you linearize the set of occupations, and then that becomes very fast. But that only solves the computational problem. It doesn't overcome the bias problem. All right, so that's the exhaustive search approach, which Card uses. And then these are the approaches, the 2 approaches which are much better, both in terms of computational savings and in terms of eliminating selection bias. Selection bias is actually the killer that makes a tree really dangerous to interpret. And I've seen people use Card and so forth, and I've seen otherwise intelligent scientists come up with all kinds of theories to explain the tree because they trust the tree. Okay, and okay, so let me just give you an example how bad this is in terms of computation. So here's a very simple example: 428 cars, only 428, and I have 13 variables. So my matrix, data matrix, 428 rows and 13 variables. 2 are categorical and 11 are ordered. My Y variable is I'm trying to predict whether a car is a 4-wheel drive, a front-wheel drive, or rear-wheel drive, right? So it's like the iris data. Iris data has 3 types of flowers. I have 3 types of drive mechanism, okay? And there are no missing values to keep everything simple. And there is 1 hammer because it's a very old data set, all right? So you would think this is an easy problem to solve. But if you look at the variables, I have a make of car, the 38 values. How many possible ways are there to split on just make alone? It's 2 to the power of 38 minus 1. That's how many ways. So you could have a Toyota. One split is Toyota on one side, everything else on the other side. Another split is Toyota and Honda on one side, everything else on the other side. You know, you just keep going like that, right? So there's a type of car. Type of car would be whether it's an SUV, sedan, and so forth. There's 6 types. Then these are the continuous variables: retail price, dealer cost, engine size, number of cylinders, horsepower, and so forth. Right. So these are the easy variables. So I ran our part. It took 36 hours. On 428 observations and 11 variables. And it loves make. because make has so many degrees of freedom, so to speak, for it to purify the nodes. Right? Now, make is not a useless variable, but it's not that important. Okay, it's unfair. It's like people running around a racetrack, you know, and you run the inside lane. Everybody starts at the same point and ends at the same point. It's unfair because you're running the inside lane, right? So I ran guide and finished in half a second. Same data set, right? It still finds make. And actually, when I look at this, so if the make is BMW, GMC, Hummer, Infiniti, Jaguar, Land Rover, Lexus, Lincoln, Mazda, Mercedes, Porsche, or Subaru, you go to the left. It turns out that this split is actually, this is quite coincidental, the same as this thing, S1. It's exactly the same. I was quite jubilant when I found that out, because even though the guide method selects make first, guide still has to find the elements of make to form that set, right? And that is still a 2 to the power C minus 1 computations, right? But what I did with guide is I sort of cheated by approximating it, because you don't really have to be super exact at every stage, first of all, because the data are a random sample. We have 400 observations, not like we have 400,000 observations, right? So you don't have to be sort of overfit the data too much, because we are going to prune the tree. We're going to use cross-validation to bail us out in terms of prediction error or prediction accuracy. Okay. Well, this is a C tree. It's so hard to see. So some of this software, the graphics are so hard. By the way, these graphics I show you for the guide, they are drawn by LaTeX, and it's run by the code. So the code that I wrote is written in Fortran, and Fortran writes LaTeX source. So when you run the software, it produces you a LaTeX file for this tree, and you just type LaTeX and it comes out. Okay. Colors and all. But this is in R, so it's, I can't even peel this apart. It's so hard to read. So anyway, by now you must be wondering, well, okay, well, how accurate is guide? Well, we don't know the truth. So I do leave one out, cross-validation, so like best I can do. So I take these 428 observations. Each time I take out one car. I build a model on the 427 cars, and I predict how well it predicts the drive type of the car. For this one is left out, right? Rotate it 428 times. The number of errors out of 428 is 74 with a guide forest. So I should mention that a guide forest is a forest of 500 guide trees, just like random forest, right? Except that random forest is based on R part with all its deficiencies. Guide forest is based on guide tree, which doesn't have these kinds of selection bias. C forest is another package that tries to do similar things as in R, and it has 78 errors. Now, good old-fashioned linear discriminant analysis is pretty darn good, right? So linear discriminant analysis has not had such a good name, but in practice nowadays it's still pretty good. So only 84 errors. The tree loses to LDA, right? So LDA, what is LDA here? LDA, we have 13 variables. So we have 13-dimensional space with 400. So imagine a galaxy of 13-dimensional galaxy with 428 stars, right? The 428 stars, and 94 of them are green color, 224 are yellow, and 110 are red. So in this 13-dimensional space, we have these stars, colored stars. LDA tries to partition them into 3 parts. That's all LDA is doing, right? Yeah. Oh, yeah, you're right. For category, I convert them to 0, 1. So actually, it's more than 13 dimensions, right? So yeah, it's actually quite a lot more than 13 dimensions. Oh, by the way, I forgot this one hammer. If I take out the hammer, this will reduce to 18 hours because of that one hammer. But this is a very old data set. Now, if I include a Tesla, it goes to 72 hours. Because the number of categories of make, right? If you increase by 1, is times 2. So that's how bad this is. So a single tree, a single tree cannot really compete against some of these more so-called flexible methods. Linear discriminant analysis allows you oblique splits, right? Whereas a tree is an axis orthogonal split, so we split on one variable at a time. So there are some constraints that make it not so accurate. But if you want to interpret that, that's the easiest than to interpret linear combinations. And this is the tree from Party. Now, logistic regression here did not converge because once you throw in all those indicators, it just cannot converge. That's why I put 2 question marks. Our part would take 1.5 years, almost 2 years to finish. I don't want to wait for so long. I don't want to dedicate a computer for 1.8 years to let our finish, because we are doing leave one out cross validation, right? So you take this 36 hours, 36 hours times 428, that's 1.8 years. Okay, and these methods, random forest and so forth, they cannot handle categorical variables in more than 31 levels. So some of these algorithms, I know I'm out of time, so let me just say what is this magic number 31? Because Leo Breiman was a very smart guy. He was also a good coder. So when he coded I think he and Jerry Friedman coded CART. You see, when you have a X which is categorical, right? So you can have its values as A, B, C, and so forth, right? So the split could be A and C and F, right? So he coded that by putting a 1, 0, 1, and then whether it's F, it's a 1. So he coded as a binary sequence. And that get can be, as long as it doesn't have more than 31 values, that's an integer. So instead of having to code these strings of zeros and ones, he would just code it to be X equals to some integer, right? But once you go outside 31, then you're in trouble. So yeah, I tend to overshoot time, so I'm sorry. I think I should end the lecture now. Thank you.